third grade either.
What did we get for our function?
I got y equals 58 times 0.9 to the teeth power.
To the teeth power. Very good. That's exactly how I would have said it. All right, so we get our functions in. I'm going to do it again on both calculators. So it might take me half a heartbeat extra in both cases. All right, now we want to know the value of the book after 6 or 5 years. So I want y of 5. That could just be a table question, or like I said yesterday, personally I like using alpha trace and then just typing in the 5 because I'm not limited to just integer values. All right, so again it's alpha trace. All right, then you get your list of y values, type in the number that you want. This allows you to put in decimal values, fractions, really large numbers, really small numbers, it doesn't matter. Right? You're not limited. So 34.2, we're talking money here, right? Yeah. So 34.25-ish.
Jake's calculator run into 34.25.
Okay, so he needs to hit mode.
Hit mode, Jake.
And then, oh, sorry, wrong calculator. Hit mode, go to float, and hit enter.
What are you doing?
Mode, float, and then so basically, this is a good rule of thumb for now anyway. And if you all hit mode, you look at the setup here, pretty much everything, it's right next to second.
It won't do anything once I hit entry.
It should already be locked in, so then you're fine. But for the first 1, 2, 3, 4, 5, 6 items, it should all be the leftmost possibility. And we'll talk about radian and degree once we get to trig, but for now, just keep everything on the left for the first 6 items there. All right. The rounding being the most important for now, because if you have it on a particular setting, it's always going to round to that particular number. So if I needed to round to 3 decimal places or 2 decimal places, it's not going to give me the option to do that. All right, it'll round it the way the calculator is programmed to round it, and that's probably not a good thing. All right, so now what I want to do is solve, because we want to know how long it's going to take to be worth less than $10. So I'm going to say, I'm going to find the benchmark, 10 equals 5, or 58, times 0.9 to the t power. All right, so for that, I had y equals. I put in the 10 in both cases. That's more for my benefit than yours because I'm using the 2 calculators again. Then I'm going to hit math. I'm going to go to solver or numeric solver. Our calculator should already be set up. Mine has the answer from yesterday still stored in. All right. I want the answer for today, so I'm going to hit alpha enter. So alpha enter. All right, that's the key. So 16.684. All right, so how long will it take for the book to be worth less than $10? Well, this is how long it'll take to be worth exactly $10. So more than or greater than 16.684 years. Just be careful about rounding, all right? Because sometimes it'll say to the nearest year, or
you'd say t is more than, right?
You could say t is greater than, you could say more than, you could say at least. Well, actually, at least wouldn't make sense because that would allow you to be exactly 16.684. Right? But as long as you get the idea across that you need to get past that number in order to be less than $10, and then you've done your job. All right, so today's lesson, let's see. I might still need calculators, so I'm going to stay over here. It just feels weird.
Quick off-topic question. How come speed sign say speed limit, shouldn't it be maximum?
Yeah.
So if I'm like driving and I'm going too fast, cop pulls me over. He's like, "Did you know you were speeding?" And I can be like, "I wasn't speeding. The limit is 45." So
Please step out of the car, sir. That's probably what he's going to say. So, yeah, because the limit could be on the high side or on the low side. So, yeah, I didn't hit the limit. I was going well over 65 miles an hour. Yeah, it probably wouldn't go over well, but, might be worth it. Just wait till you have your senior license before you do that. Right? Because my understanding is that if you get a moving violation while you're on your probationary period, it's an automatic suspension. So if you have your junior license and you get a moving violation, automatic license suspension. When you get your senior license, then it's a different story. So if you're going to mouth off to a cop, wait until you have the senior license at least. And a good lawyer. So anyway, arithmetic sequence. I know it says arithmetic, but for whatever reason we pronounce it arithmetic in this context. Yeah. Yeah, it makes it sound fancier than it really is. But they tell you to consider the sequence. Right, I am going to consider it. All right. Check. I have considered it. Yeah, it's kind of annoying. I don't like that terminology, but it seems like every math textbook, exam, blah blah blah, they like to write it like that. It's just weird. But really, when we talk about considering something, we're talking about thinking about the important characteristics that are existing within a situation. So, like for example, if we're talking about a graph, we might talk about slope. We might talk about intercepts and things like that. If we're talking about a sequence of numbers, we're talking about the transition from one number to the next. So how do you get from a 1 to a 4? How do you get from the 4 to a 7, the 7 to a 10, and so on? At 3, all right? So what would be the next number in the sequence? 16, all right? And that's because we're adding 3 every time. All right, for each consecutive value, from one movement to the next, we're adding 3. All right. And just to kind of steal my own thunder a little bit here, if you're ever just adding a consistent value from one term to the next, what you're dealing with is called an arithmetic sequence. All right. If you're multiplying by the same number to get from one term to the next, it's called the geometric sequence. That's a lesson down the line. All right. So to define an arithmetic sequence, we say that you're adding the same number to get from one term to the next. All right, so you're adding the same number to get from one term to the next. An important thing to think about is the relationship between this and other instances in which we did pretty much the same thing. If we had a particular start value, and then we added a number to that and got a new value, and then added a number to that and got a new value, and so on, what kind of function are we dealing with?
Depends on if the numbers are the same.
Okay, so they're the same.
Oh, linear.
Then it's linear, all right? And that's really what's happening. And this is the good news. An arithmetic sequence forms a linear function. So the good news behind that is we know how to handle linear functions. There's nothing new here. Right? All we have to do is kind of convert the new notation to what we already know about linear functions. All right? Because what we have is a fixed component and a variable component in a line. You have the y-intercept, and then you have the part that relates to the slope. All right? If you know those two pieces of information, then you have the line. All right? It's the same idea with an arithmetic sequence. All right? But the notation is a little weird. And actually, in all honesty, when I was first learning about this, I had a hard time with the notation. I didn't really understand it because I get fixated on little things like, why do you have this notation when the other notation works perfectly fine? Like, if I learned all about that, and this is the same thing, why do I have to learn it this way? I'm still working on that. I have no idea why. Right? There are some calculus-related concepts, and I hate to go back to that all the time. There are some calculus-related concepts that are better served in this notation, but until you get there, I don't see what the need is to have this subscript notation and things like that. But for some reason, the state seems to think it's important, so now I have to pretend it's important. So yeah, it's like really important. You got to know it. Your life will never be the same afterwards. The terms of the sequence are referred to using a notation where the subscript number refers to the position of the term in the sequence. These terms and patterns can be expressed as a formula. Right? In the sequence, 12, 24, 36, blah, blah, blah. An explicit formula can be written as a sub n equals 12n. Like, it just sucks the life out of me wherever I see that. Right? Because I would prefer to write that as y equals 12x. Right? But if you kind of make the transition in your mind to say, okay, so what you're telling me is that the a sub n is really the y, the n is really the x, and the x is just telling me the position within the sequence. All right, I guess I can do something with that. All right. So if I knew the fifth term, or if I wanted to find the fifth term, I can use this model to help me come up with that. All right. I would know without actually having to count by 12s that the fifth term would be 60. All right. So the fifth term would not be hard to come by because I remember these back in elementary school when I was in elementary school, where it's like you had the shapes first, right? You had like the pattern of 3 shapes. And then they gave you 2 more shapes after that, and they said, what would be the third one? And you just had to remember the pattern. Then eventually they did that with numbers. So it would be 12, 24, 36, blah, blah, blah. And then they would say something like, what would be the 10th term in the sequence? And one way to do it would be to say, okay, 12, 24, 36, 48, and so on. And you'd get there. But if you have this model, then you're not limited to just what you can count. If they said find the 3,000th term in the sequence, I don't have to count by 12s. That would take the whole class period. I mean, that would take like, I don't know, like the whole day. 3,600 seconds in an hour. So, assuming you can come up with a new number every second, it would still take you over an hour to do that. No, it would take you less than an hour. But there's no way that you could say each unique value every single second. So, probably like an hour to 2 hours to come up with all the possibilities, right? So it would take forever, or it would seemingly take forever. All right, but just multiplying 12 by 3,000, that's not hard, right? Especially if you have a calculator. So we represent it using this notation, but again, y equals 12x feels more familiar, feels like it would be more useful, that it makes more sense. This is just not the most appealing thing to look at, but it gets the job done, and we do have to use that notation, right? So, number 1, write and label the first 3 terms of the sequence. A sub n is equal to 2 times n minus 1, right? So this is the way I like to do it, to get around the weirdness of the notation. I'm going to list out the n values. Then a sub n is 2n minus 1. All right, so this is my a sub n. I'm just going to draw an arrow to it. All right. So the first term, and I'm not going to write this, but the first term would have a value a sub 1. The second one would have a value of a sub 2, and then a sub 3. That's just telling us the position within the sequence. I'm not overly interested in that right now. What I want to know is the value at that particular position. All right. So all I have to do is plug in a 1 for 2n minus 1. What do I get? 1. All right. What do I get when I plug in the 2?
3.
3, and then 5. All right. The good news is because we recognize this as a linear relationship, you don't really need to do the calculation. So if you were plugging in, you plug in the 1, right? We got the 1. But then if you plugged in the 2 to get the 3, and then plugged in the 3 to get the 5, that's not the best way to do that, right? Because in a linear function, the slope tells you to transition from one term to the next. So once I get the first value, I forget about the numbers and I just think in terms of the slope, all right? To get from the first to the second, I'm increasing by 2. So 1 plus 2 is 3, plus another 2 is 5, all right? So if I needed to come up with the 10th term of the sequence, I'm not gonna type in 10. I'm just gonna say, okay, 1, 3, 5, 7, 9, blah blah blah, and I get to the 10th term that way. It's when I have to do like the 50th term of the sequence. That's when I go to the rule. All right, you gotta think strategically about this, because sometimes the quicker way to do it is the way that you would do it in elementary school or middle school. All right, just by counting. Right, and sometimes it's by using the model. All right. So in number 2, where they say find the 3rd term of the sequence, do I want to make an entire table for that? I don't know. Maybe you do, maybe you don't. Right. But number 3, it says write and label the first 3 terms of the sequence. So you actually have to do it there. So in number 2, I would look at this and say 3rd term of the sequence. So that's an n value of 3. So I'm looking for a sub 3. This is really just function notation, just in a slightly different form. The subscript is like the of x part. So negative 3 times 3 plus 5. So you get a negative 4. All right. Now this has a negative slope, so my terms should be decreasing as I go down the line. So my first term should be bigger than my second, which in turn is bigger than my third, and so on. All right. It's in the next one where I have to write and label. So the n values, first 3 again, 1, 2, and 3. But now my sequence is defined by 5n plus 1. So again, really, you have to think of this as, so think of it as the x value and the corresponding y value. All right. We'll talk about what this looks like graphically down the line, but the one difference between the graphs of this function, or these kind of, you can call them functions, but these types of situations and a linear function, is that these would actually not be connected. So if I were to plot these points, so 1, 1, 2, 3, and 3, 5, on a set of coordinate axes, I would not draw a line through them. Unless you can tell me what the 1 point second term would look like. Like if I told you to line up, there's roughly, I'll say 20 people in the class. If I said to line up and I was counting off the folks in the class, if I were to say, all right, I need the first person, the 5th person, and the 7.8 person. What are you getting on the 7.8 person? You're like, so I want the 7th person, the 8th person, or like some sort of mixture of the two? That's weird.
0.4 of each.
0.4 of each, so like chop off a limb and, throw it in Voldemort's, what you call it? Oh man. What's the bowl that you mix potions in? No, it's not. Cauldron, thank you. Yeah, Voldemort's cauldron. And like in Goblet of Fire, where Peter Pettigrew, it's supposed to be a children's movie, but he chopped off an arm, put it in there, threw in a little Harry Potter's blood, and all of a sudden, milky skinned Voldemort came out and started lots of trouble. All right. We'll have to add it to the list of things to watch in senior year. So flash forward to senior year this time, when you're sitting in my calculus class, assuming I'm still teaching that then, you'll have to remind me.
Hey, we wouldn't be in calculus though. Unless we're smart.
Well, you are.
But
Well, I'm not going into calculus.
You're not?
Well, I don't know.
Don't we take pre-calc?
Let's see why not.
Wait, yeah.
Oh, you could have me for pre-calc too.
I'll only go to
Bottom line is you'll have me at some point again, most likely.
I'll only go to
So when that happens, senior year most likely, remind me, Harry Potter, Goblet of Fire, we'll watch the whole thing. All right. What do I get when I plug into 1? 6. All right. I'm not going to plug in the 2. I'm going to take note of the slope. I'm just going to add 5. Right? I'm going to add 5 again. All right. At the end of the day, is it easier? Yeah, slightly. Is it earth-shatteringly easy? No, because you have a calculator. So worst case scenario, you type your function in and go to the table and get the values. All right, but it's nice to be able to recognize these things. All right, number 4, the 12th term of the sequence. All right, I don't want to list out n equals 1 all the way to 12 just to figure out the 12th term. So this is a case where I would say I have an n value. Oops, that's not an arrow. Poor quality arrow anyway. So a sub 12 would be equal to negative 12 plus 6, negative 6. Same idea for the 8th term of the sequence. A sub 8, 1/2 times 8 minus 3, so 4 minus 3 is 1. So, of course, we have another formula to memorize. But it's actually really not a new formula. It just looks very much like it is. It looks like this devastatingly complicated formula, but it really is not in any way any more complicated than something that we've already done. Remember, arithmetic sequences are another way of saying linear relationship. All right, so this is somehow the equation of a line. All right, so let's actually take a look at that off on the side here. The equation of a line. I'm going to use the point-slope form, which I've been saying all along is the most important form. Y is equal to m times x minus x sub 1 plus y sub 1. All right. Now, I'm going to change it a little bit. I'm going to write it as y is equal to y sub 1 plus m times x minus x sub 1. All right, so nothing complicated there. All I did was swap the 2 terms. I took this bad boy and switched it with the x, so y sub 1. All right, so nothing too crazy there. But look at the structure of it. Look at how it's made up and compare it to what we have here. All right, it's the same thing. All right, so the d value must be the slope. All right, so I'll actually just tackle that first. The d value is, well, I could say the slope, but it's really the change from one term to another. All right, so n is taking the place of x. All right, x talks about how far you're going out on the x-axis, but I equated it to the n values on the previous page. Those n values are talking about the term within the sequence. All right, so n is really talking about position or term in the sequence. The only part of this that becomes weird in terms of the notation is I'm starting off with a sub 1. A sub 1, well, does that mean y-intercept? Not necessarily. Well, y sub 1 never meant y-intercept anyway, so that's fine. But what the a sub 1 is talking about is the initial value in the sequence. Yep. All right. So the difference between this and, for example, a y-intercept is a y-intercept would take place when the x value is equal to 0. You can't have a 0th term in a sequence. All right. If I were to, I mean, there is a way to do it, but when you're actually counting values, if I were counting people within a room, I would say, okay, who's my 0th person? Like that doesn't feel right. All right. So we typically define an arithmetic sequence to start with a first term, not a 0th term. So that's a slight little departure, but nothing earth-shattering because it's still going to work the same way. All right, so when it comes to actually writing an equation, I just need these 3 values. Once I have these 3 values, I have my explicit formula. All right, so very easy to identify. If they give you the sequence, the a sub 1 value. The d value, again, is the change from one term to another. So d in this case would be what?
4.
4. All right. If you know it's arithmetic, all you have to do is find the difference between any 2 consecutive values. All right. Just make sure you get the sign right, because this one is increasing by 4. If it were decreasing by 4, it would be negative. All right. There will be some, I don't want to call them trick questions, but some sequences down the line where it's not arithmetic, but it might look like it. Maybe the change in values are the same initially, but maybe the 4th term is like 18. So it goes plus 4, then plus 5. If it's not consistently increasing by the same value across the board, then it's not arithmetic and you have to use a different technique. But we'll talk about what that technique looks like down the line. Yeah.
If it's not like that, is it like not considered linear then?
Correct. All right, and so everything else is good to go. So a sub n, that takes the place of y in our way of thinking, would be equal to 5 plus 4 times n minus 1. All right, because n takes the place of x in our way of thinking. All right. Now, personally, I like to give it a quick test and make sure that it's going to give me, well, you don't have to test it for each one, but maybe test it for one of them. Like the 4th term should be 17. So if I plug in a 4 here, I get a 3 times 4 is 12, plus 5 is 17. All right, so we're in good shape. You don't, like I said, you don't have to test it for all of them because that could be a waste of time, but at least test it for something. Right? You get to a point where you have enough experience with this where you don't even have to write these little notes because you identified the start and the d value and you have your model. But I'll write it anyway. What's my d value here?
9. Oh, no.
Negative 2. All right, d for difference. So 9 minus 2 times n minus 1. I'll pop in a 4 for n. 4 minus 1 is 3, times negative 2 is negative 6. 9 minus 6 is equal to 3. All right, so we're in good shape there. All right. So, number 8, a sub n, negative 7 plus 3 times n minus 1. Number 9, a sub n, 1/2 plus 1/2 times n minus 1. Yeah, I don't think this is happening right now. Of course, is we do it by hand and then we do it on the calculator. So I'll do the first one by hand with you. You can see just how wonderful the process is, and then I'll show you the calculator approach. And then you can decide for yourself which one you like more, with the hope being that the calculator way is the way that you like more. All right, so the first 4 terms of the sequence with a sub 1 being equal to negative 4, and a sub n equals a sub n minus 1 plus 5. It's like, what is going on here? All right, so where you ever are bound for n, or a constraint if you want to call it that, n is greater than or equal to 2. All right, so what that's telling me is that if I were to take a 2 and plug it in for n, I would get a sub 2 is equal to a sub 2 minus 1 plus 5. All right. So that being said, we already know what a sub 1 is, and I should write that down because it's already written, but I'll write it down here anyway. A sub 1 is equal to negative 4. I'll draw a little partition there. All right. So they wanted the first 4 terms of the sequence. They gave us the first. We just have to come up with 3 more. All right. We know 2 minus 1 is equal to 1. That's not me being a wise guy. It's just that's something that you want to do in this process. And that's what really defines the recursive model, because it's calling upon a past piece of information to generate a new piece of information. So by plugging in a 2 for this equation, everywhere I see an n, I get a sub 2 is equal to a sub 1 plus 5. Well, a sub 1 was given as negative 4. Plus 5, which will give us a 1. So I now know what the second entry in my sequence would be. It's going to be a positive 1. But when you really think about it, that's a sub 2, yeah. When you really think about it, that kind of means that you didn't have to do any of that. We'll do it for one more calculation, and I'll show you. A sub 3 is really a sub 3 minus 1 plus 5, which is the same as saying a sub 2 plus 5, which is to say that we're taking the 1 and adding 5 to it, which gives me a what? 6. All right, so all this formula is telling us to do is take your previous answer, add 5 to it to get your new answer. All right, so take the previous answer, negative 4, add 5 to it, you get the next one. Take that previous answer, 1, add 5 to it, you get the next one. So what's a sub 4 going to be?
11.
11. So I could write all the work out if I want. I guess I will, just to kind of complete it. So I have the first 4 terms of the sequence. It's just probably not the most entertaining thing to do in the world. All right, so what a lot of folks will do is they'll write it as a table instead of showing all this work. I mean, you show the work when you're asked to show the work. But if you're not, and you just have to come up with a sequence, there's another way to do it. One way would be to say my a sub 1 value in the next problem is equal to 6. My a sub 2 value, 3 and 4 are the ones that we need to come up with. All right. So you could kind of reason it out if you want, but this model is telling you what to do. Take your previous answer. In order to get a sub 2, take your previous answer and subtract 8 from it. So negative 2, negative 10, negative 18. All right. We have the same kind of drawback here that we had when we were dealing with other types of exponential and linear equations. If the numbers get big, do you want to do it out this way? Probably not. All right? So we go to the calculator. And the calculator becomes a really valuable resource because there's a bunch of different ways that you can do this on your calculator. All right? I'm just trying to think, because there really is, off the top of my head, 1, 2, 3, You have 4 different ways to do this on the calculator. I'm not going to show you all 4 ways because it's just destined to be confusion. I will show you what I think is probably the easiest way. It may be the easiest way. We'll see. Pretty important when you think of it that way.
So you hit alpha x, like which x?
Alpha, the xt theta n.
Don't work for me.
So this bad boy.
Yeah, don't work for me.
Okay, so you'll need an update. So writing the recursive formula is actually not bad. It's just the notation is a little weird. But really, when you think about it, it's kind of along the same lines as what we did before. Now, this is an arithmetic sequence situation. We still have to deal with geometric. All right? So I need my start value, and I need the change. All right? So from term to term. So my recursive formula is going to be a sub 1. What's my start? 5. And a sub n is equal to a sub n minus 1 plus, what's the change from point to point? 4. Where n is greater than or equal to 2. All right, there's also the function notation. So I kind of stole my own thunder a little bit with the calculator approach. F of 1, so this is an OR situation, because you might be asked to write it in subscript notation or function notation. F of 1 still means the initial value, 5. We just write it as f of n equals f of n minus 1 plus 4, where n is greater than or equal to 2. All right, this approach, the one I wrote in blue, is more closely aligned with the way we do it in the calculator, except they're using u's instead of f's. Yeah. All right, so when you think of it that way, you kind of have to know this anyway. So what's the adjustment between that approach and the calculator? Very minimal. All right, the one thing that you always have to keep in mind when it comes to using the calculator is making sure that you put the calculator in the mode that's most useful for you to be successful. All right, so yeah, after you do a problem like this, put it back into function mode. All right, so familiarize yourself with that mode menu because it's that important. All right, so numbers 13, 14, they're not anything different. Even 15.
So what would be in like both notations, function and...
Only if you're asked to.
Okay.
Only if you're asked to.
In the box up here it says a sub n subtract 1, but we wrote it plus 1.
I wrote plus 1?
Oh, wait, just kidding.
Oh.
Never mind.
All right, so for like number 16, sometimes they give it to you in slightly different notation, but that's nothing really crazy. An arithmetic sequence is given using the recursive definition here given. What is the value of d of 4? So what we want to do there is really just evaluate what we've been given. But again, if the numbers are complicated enough, maybe you go to the calculator. So the idea being that you can always have that option to kick over to the calculator and just go right to a table. All right. So for a single value, I don't know. I would think by hand is probably the way to go. If I'm looking for the fourth value, or sorry, D4, that's equal to D3 plus 3. All right. The problem with that is D3 would be equal to D2 plus 3. And in turn, D2 is equal to D1 plus 3. All right, it's for this kind of problem where I say, well, maybe you do want to go to the calculator, but you don't really need to, because you're just working backwards in order to figure out what the progression is. All right, so you know what the relation is. You could just count, but you can kind of see how, if again it's the 75th value, this could be problematic. Like you don't want to do that. All right, but I know that d sub 1 is equal to negative 4, so we're looking at negative 1, 2, 5, so we get the 5 that way. So we define our model this way, but then we perform our calculations this way. Personally, I think that it's for this kind of problem that the calculator technique is your big sell. All right, because you look at something like this, and again, if they say d sub 75, even the idea of saying, all right, well, what am I plugging in? What's getting substituted? As opposed to just going to an entry in a table. I mean, there's really no contest there. All right, so that's my big selling point. If you're not buying it after that, you're not buying it. All right.